So we saw in the last video and in the last set of homework problems how to go in and use the Riemann sum to get an estimate of what the area would be, under a curve. Okay, so we talked about the upper and lower sums and how to approximate. We're not finding the exact area, just an approximation of it. Well, if we were to take the number of rectangles and make the number of rectangles smaller, right? So the width of each rectangle gets smaller and smaller. Let me draw you a little example of what I'm looking at here. As a matter of fact, let me take you to the book. I think your book does a much better job of helping you visualize what's going on here. So scrolling down, here we go. Okay, so we have a shape. It's kind of it's an increasing function. It's almost like you have the left side of a frowny face and then a smiley face put together, right? So it's kind of an increasing function. There's a little dip in the middle there, and we have four rectangles right here, all right? And so you'll notice that if we're finding the approximation of the area between A and B in this graph right here, you'll notice there's a lot of this area that gets left out of our rectangles. And so what we can do is increase the number of rectangles, right? So we still have A to B, but now we have more rectangles. And what happens is that the amount of space that's not covered by a rectangle decreases. And then if we increase the number of rectangles even more, now we get even smaller and smaller spaces where we don't have something taken by the rectangle. So ideally, we would want an infinite number of rectangles so that we don't have any of this leftover space, right? Well, if we're going to have an infinite number of rectangles, that means we've got to go in and we've got to find the limit as the number of our rectangles approaches infinity, okay? And that's what we have here. We have a Riemann sum, right? And we're finding the limit as the number of rectangles approaches infinity. You had just finished doing problems where we started with, we had four rectangles, right? Where we start at one and we go to, so we have four subintervals. Well, now we have an infinite number of subintervals. And what we want to do is be able to convert our limit definition of a Riemann sum into a definite integral. Okay, so we're going to talk more about the definite integral as we go, but the definite integral is going to act just like this infinite sum. Okay, and we're gonna find out what the definite integral is from A to B here. And our job in this video is to just kind of go from this limit definition to the definite integral. There are a couple of things we want to point out. Okay, so f of x is called the integrand. It's the thing that I'm going to take the antiderivative of. Dx indicates that we have a function whose variable is x, right? It's called the variable of integration. And then a and b, the things that go here and here, those are the limits of integration. So right here, if I said, what is the integrand in this problem, you would tell me that the integrand is just this piece here, right? The 2tv squared. And this is considered a function with respect to v because we have dv, right? So I know that we have some t's in there, but we would be integrating this with respect to v. So let's talk about how we would go from this limit definition to this integral definition, okay? You can see here that we've defined what this interval is, right, from 0 to 3. We've defined that for you. And our job now is to say, okay, well, how do I take this information and create that integrand, right? So f of x sub I, right, that's just a fancy way of saying f of x to the third minus 6x squared, right? And that's going to be what our integrand is. We're just going to drop the I, and this is what we're going to use to write that definite integral here. You have some problems in Newton where we work through a few of these, and you can get some more instruction there in Newton. You can obviously reach out to me if you're having issues, but really what we want to do is just help you see that the definite integral is an infinite sum, and we're going to talk about how are we supposed to go in and find out what that equals. That's what we're going to look at in some of the subsequent videos that we have in this chapter before we wrap up Calculus 1.